Welcome back. The series of counters. The previous sessions we discussed about introduction to the counters, different types of counters, 2-bit up counter, 2-bit down counter, and after that we discussed about the 2-bit up and down counter with the combination circuits. Now in this session I would like to discuss about modulus of the counter, or else we can say it's a mod. Suppose if you are using 2-bit counter, it is called mod 4 counter. Why? Because we can count up to the states of 4, 0, 1, 2, 3. And for 3-bit counter, it is also known as mod 8 counter. Why? Because we can count the states 8 from 0 to 7. So in this way, the modulus of the counter is the number of states of counting sequences. That means if you take one example, so here I will take mod 6 counter. So mod 6 counter is nothing but whenever we count from 0 to 5, that means 6 states, then it is known as mod 6 counter. So in this class we would like to design this mod 6 counter. That means we need to count start from 0, 0, 0 and 0, 0, 1, 0, 1, 0, 0, 1, 1 and 1, 0, 0 and 1, 0, 1. So here 0, 1, 2, 3, 4, 5. For the next state 6, it is actually 1, 1, 0. But I need to make this 1, 1, 0 forcibly to 0, 0, 0 for the mod 6 counter. Why? Because after counting of 6 states, after counting of 5, when I am triggering the clock, flip-flops has to be clear to zeros. I am forcibly making all the outputs of the flip-flops to 0. Then again the sequence will be continued up to count 5. That means again it will repeat it to 0, 0, 1 again up to and so on 1, 0, 1. So this is an example for mod 6 counter. And the relationship to the flip-flops is, suppose mod 6 counter, we can design mod 6 counter with flip-flops are 3 required. Why? Because mod 6 counter, we cannot design mod 6 counter with 2-bit counter. Why? Because the maximum number we can count from the 2-bit ripple count is 3. 0, 1, 2, 3. That's why the relationship to the flip-flops to the modulus is the maximum possible modulus of the count is determined by the number of flip-flops used. That is 2 power n. Mod 6 counter. Let's see here how this. How can I make this forcibly to 0 means there is suppose if I take a flip-flop here. So here I have a clock pulse and here one, and here it is also one option is there. This is clear pin. This pin is known as preset pin. Suppose if I want to make the output of this flip-flop, suppose Q, if I want to make this Q as 0, irrespective of the input, I just give clear input as 0. If I given clear as 0, then irrespective of the input, the Q will become 0. And if this is preset, if preset is 0, irrespective of the output, the Q will become 1 for preset is equal to 0. If clear is equal to 0, the Q will become 0 and preset is equal to 0, the output will become 1. So in this way, I can make forcibly the required output to 0. So let's see this modulus of the counter, modulus mod 6 counter. So you need to understand that at this count, whenever the output reaches 110, it has to be make it to 0, 0, 0. And remaining things are same. So I have taken the same JK flip-flop. It is J1, K1, Q1, J2, K2, Q2, and J3, K3, Q3. And I connect all these clear button. So I need to make all the clear buttons of the flip-flops have to be activated at a time. And I will give this clock pulses to each. For this first flip-flop I have given a clock pulse, and this will be given to this, and this output of the flip-flop given to this clock pulse. Okay, and JKs are given as inputs as 1 for the toggle mode. Inputs are given as 1. Okay. Now let's design these flip-flops, this MOD-6 counter. So whenever I reach the MSB, so that is Q3, Q2, Q1. So whenever I reach this Q3 as 1, 1, 0, I need to make this forcibly to 0, 0, 0 by using 1 AND gate. For this, Q3 is 1 and Q2 is also 1 and Q1 is 0. So that's why I need to use one NOT gate, that is 0 will becomes again 1. If I given this output of this NAND gate to this clear button, then automatically this clear will be activated, that it will becomes 0. Then all the flip-flops will clear to 0. That means this Q3 has to be given here and Q2 will be taken from here and Q1 will be taken from here. So whenever the output comes as 1, 1, 0, whenever the output comes as 1, 1, 0, from this NAND gate, it will become 0. Then the clear button will becomes 0, 0, 0, so that the flip-flop will be set to 0 again. So this is the technique we can use in the MOD-6 counter. Similarly, we can design any modulus of the counter, suppose MOD-4 counter or MOD-7 counter, anything. Suppose if you want to design a MOD-7 counter. So what I need to do, so it has to count from 0, 0, 0 to 0, 1, 2, 3, 4, 5, 6. So this is the maximum count for the modulus of the count, MOD-7 counter. So for this, it has to be 1, 1, 0. If I given the next state, that is 1, 1, 1, it has to be forcibly to 0, 0, 0. So I have given this, if I remove this NAND gate, sorry, NOT gate, that means if I given the connection like this for the output of NAND gate, Q3, Q2, Q1, that is 1, 1, 1, then it will become 0 again. So in this way, this is the connection diagram for MOD-7, modulus MOD-7 counter. So in this way, we can design any modulus of the counter. If you see the timing diagram, suppose if I given a clock pulse like this, so clock pulses, so negative edge triggering, the clock pulses are 1, 2, 3, 4, 5, 6. So suppose I want to know the Q1 output, so this will be 0 up to the first clock pulse or first triggering point, and like this. So we already discussed all these things in the previous classes. If you don't understand, please go back, watch this video so that you can understand better. So this is the clock pulse of Q1. So whenever this sixth triggering is there, we are making this forcibly to 0, 0, 0 for this. Similarly, when you draw for Q2, it is like this up to this point, and up to after this sixth pulse, after this sixth triggering, it is also big 0. So we are making forcibly to 0, and similarly for Q3. So in this way, we can design any modulus of the counter. Right? Thank you. Have a nice day.